Hey guys, what's up? It's Zach here, doing this for the Breakthrough Junior Challenge. And today I'd like to discuss with you the concept of virtual particles.
Now, you may be asking, what is a virtual particle? That's a pretty great question, to be honest. Um, Physicists still don't quite understand the concept of virtual particles, but what we know of them is that they live beyond their means, and that what that means is they actually steal their energy and their mass for a certain amount of time, which defies many of the basic laws of physics. Now, you may be familiar with Heisenberg's uncertainty principle, and this states that the momentum and the velocity of the and the position of the particle actually is related to a constant. This is actually a Planck's constant, and so because this is a constant, what this means is that if we know its momentum very well, we actually don't really know its position. We can't set it to one position, and if we know its position very well, we actually don't know its momentum very well. So there's a relationship between these two. Now, conveniently for us, virtual particles exhibit a very similar phenomenon, and this is delta E times delta T equals the same constant. Now, delta E is the spread of energy, and delta T is the time. So, for very short periods of time, these particles can actually steal quite a bit of energy. However, as the time increases, these particles must release, in a sense, this energy back to the universe. Here we have the standard energy-momentum relation, which is m squared c to the fourth equals e squared minus p squared times c squared. Now, a lot of people know this as E equals mc squared, made famous by Albert Einstein, and that's neglecting the momentum of a particle. But virtual particles do not obey this law. The reason why is because their kinetic energy oftentimes is negative. So I've given you a lot of equations about these virtual particles, but I haven't really talked too much about what they actually are. And actually, in classic physics, these particles were actually just seen as forces, excitations of photons or different particles. In fact, they actually only appear in certain calculations in physics, but not as the essential particles. For a very long time, they couldn't actually detect the particles, so they just labeled them as forces. In fact, many forces would not be possible without the existence of these virtual particles. This here is called a Feynman diagram, and this helps to explain the presence of these virtual particles. So picture this as a particle with momentum p, and this is a particle with momentum p2. This interaction right here represents the virtual particle. After this virtual particle with momentum k has left p1, p1 exits with momentum p1 minus k, while particle 2 will exit with momentum of p2 plus k. And this represents this virtual particle being transferred between these two. This can work with quarks as well, except this would be a virtual gluon, and for electromagnetic forces, this would be a virtual photon. Now, this stuff gets really interesting when we start talking about these virtual particles in a vacuum. These bosons in this vacuum actually are continually changing in the number that they have. So the presence of these bosons, there's a different amount of them each time you observe them. This is somewhat due to the uncertainty principle, but this can also be explained by virtual particles because these virtual particles are constantly stealing bits of energy from the universe and creating themselves for small fractions of seconds and disposing of themselves then, or releasing themselves back into the universe. And so the number of bosons are constantly changing. thing these virtual particles inside the vacuum help explain is the Casimir effect. And this is a phenomenon in which two metal plates that are uncharged, spaced a few nanometers apart, will actually exhibit a electromagnetic force upon the other plate. And the reason why is because there are these virtual particles interacting between the two plates, even though they don't have electrical charge. Now, some would argue that these are van der Waals forces, but the presence of the virtual particles helps to explain van der Waals forces. So, in a sense, it all comes back to the virtual particles. Our belief with many physicists is that virtual particles actually exist with a particle and an antiparticle, and that the short time that they exist, they actually annihilate each other. Stuff gets even crazier when you start talking about inertial planes of reference and an accelerated frame of reference. The best way to explain this next effect is actually using a pretty simple comparison, and that would be if you took a thermometer, a standard thermometer, and waved it around, accelerating it, you would actually see that the thermometer would be a non-zero temperature. In a similar way, imagine a vacuum, and imagine that you are in an accelerated frame of motion looking at that vacuum. The question would be, what would you see? And interestingly enough, as you are in this accelerated plane of motion, these virtual particles take on the appearance of actual particles. And this is due to your accelerated frame of reference, giving these virtual particles, in a sense, extra energy to become, or to appear to become, real particles. I'll give you another example of how some of these virtual particles work, and specifically I'm going to talk about virtual photons. These virtual protons actually create an electromagnetic field. So let's say, just for an instance, that this space right here is actually an electromagnetic field. If I were to put my hand in this field, I would not be able to move it no matter how hard I budged. These virtual photons, which exist within this electric field, actually provide the momentum, much like in the Feynman diagram, to actually adhere to atoms within my hand and create enough momentum to stick my hand onto the wall. Sort of similar to van der Waals forces, but much, much stronger. Finally, I want to talk about what makes a virtual and an actual photon or particle different. To be honest, there's not that much of a difference between the two. The notable difference is that virtual photons or particles destroy themselves within a matter of fractions of seconds. Now, actual particles may exist for longer periods of time, but in the end, they will end up destroying themselves as well. So, in a sense, you can think of a real particle as being a prolonged virtual particle. Virtual photons and particles are much easier to create, however, because they only steal the energy from the universe. They don't actually need the total amount of energy to create themselves, because they only create themselves for very short periods of time. So any electron in an undisturbed state could potentially give off a virtual photon. Yes, that's all the time I have for you right now. I hope you enjoyed this little mini lecture, I guess, and I hope you understand a little bit more about virtual photons and particles and how they play such an important role in our lives today. I appreciate your support, and I hope my video was informative. Thank you for listening.